All right, so let's see if we can get this to work. All right, graphs and transformations. So we've done lots of transformations already when we've been working on, in Algebra 2, we did a lot of transformations. We did them with the quadratics. Okay, if you think about the biggest thing that we've just done is we did transformation form for quadratics. So this form we were working with for the quadratics, when we did f of x equals x minus h squared plus k, that's transformation form because we've taken the parent function x squared and we've moved it horizontally h, vertically k, and then we've also put a in here so that we did, with a we had either stretches or compressions vertically and then reflections if it was negative. Okay? So we've been working with transformations when we were doing transformation functions. So graphs and transformations, here are a main 9 different parent functions. Okay? There is the constant function, which is just a horizontal line, f of x equals 1. There's the identity function or linear function, y equals x. Absolute value, the greatest integer function, which once again is a round down function. Quadratic, cubic, what do we call this one? Reciprocal function, okay, 1 over x. You've got the square root function and the cube root function. Those are the main parent functions. So what we're going to be doing in this lesson is that we're going to go through all the transformations because we've talked about them before. In the Algebra 2 book, Algebra B and C, we did it with x first of all, okay, with the identity function. Then we did it with absolute value, and then we did it when we did the quadratics. Yes, Caleb?
Why is the bottom one on the bottom right, the cube root function, why is that a function? It looks like a line would go right through it.
Because this does not, it doesn't go back. The graph comes along here, moves up, and goes. It's just they're very close together there. So it's kind of like when you graph x squared, looks like that. But if you graph x to the 4th, when it comes down here, it actually almost looks like it stays along the x-axis a little bit longer, but it really doesn't. All right. So all the parent functions are just where we have x there. And then we're going to put h in, where we go move horizontal transformation. Put k in, we do vertical transformation. And then we'll be doing a and b. So we'll be doing horizontal shifts and stretches and vertical ones. All right. So first of all, and on your handout you've got, we were looking at transforming x squared. Okay. So first of all, we're going to do vertical shifts. All right. Vertical shifts are, we're adding a constant, and they use c here, but usually when we do vertical shifts, we've looked at using k, because as far as that goes with our transformation form. But we're actually going to put it in order because we're going to be doing, there's 4 different possibilities that can happen. You've got vertical shifts, horizontal shifts, vertical stretches and shrinks, and horizontal stretches and compressions. And so we're going to have end up using the letters A, B, C, and D, but they use C quite a bit. So first of all, vertical shift just means we're taking the function and we're adding or subtracting something to it. And as we get into this, the reminder that if the function itself is being affected by it, it's something, so it's going to be inside parentheses under the radical, okay? That means it's going to be something horizontal. If it's outside of the parentheses or outside of the function itself, it's going to be something that happens vertical. And we'll get more specific. So graphing x squared minus 4. So graphing x squared minus 4, all that is what? Okay. Moving it up 4. So that would be x squared minus 4 is going down. Sorry. So it would look like this. What did I just do? I put the function up here, and then by putting the function up there, then I could just drag it onto my graph.
Is it the same slope, like it goes up and whatever one?
Yeah, so one of the things you need to think about, that's a good question. So one of the things you need to think about is that while you're doing these, think about rates of change to be able to graph them easily, okay? So I can do stuff without my calculator. So with the standard graph of y equals x squared, if we look at the table, that we can see that if I go from 0, 0, okay, so I plot the point 0, 0, okay, or wherever my y-intercept is, then I'm always going to go, as I go up 1 for x, y goes up 1. As I go up 2 for x, y goes up 4. Okay? If I go down 1 for left, or go to the left 1, it goes up 1. If I go to the left 2, it goes up 4, because I'm squaring those numbers. So with this graph here, then from this new y-intercept I have, I'm going to go over 1 and up 1. If I go over 2, I go up 4, because it's squared. Over 3, we would go up 9, and so on both ways. So you can think about what's the easiest way to make that new graph. Okay? So for instance here, for h of x equals x squared plus 3. So for this one then, I'm going up 3, right? And it's a quadratic. So then I can go over 1 and up 1 to make a point, both directions. I could go over 2 and up 4. And then I have those points to make my graph as accurate as I can do. To make it an accurate graph. I'm talking about from the vertex point. Yep. Horizontal shifts. Now notice the one thing is that with this vertical shift, like I was talking about, it says f of x plus or minus some number for a vertical shift. Where for when it's horizontal, it says f of x plus c or f of x minus c. That adding or subtracting c is inside the parentheses. So that means that it's going to be a horizontal thing. And not only that, but when it's horizontal, it's actually the movement is going to be the opposite, right? So if it says plus, I'm going left, yep. And if it says minus, I'm going right. Okay. It's a quadratic. Yep, I'm sorry, we didn't say that. Okay, it says state the parent function. The parent function here is a quadratic because it's x squared. Right. So, yes, Caleb. Is the main thing. Not necessarily. Let's look at this one then. Okay. All right. So this one has a radical here. Okay. All right. That's a square root function. Okay. So the parent function there is the square root function. It's just there's something that's happening to that. With this one, square root of x minus 3. Okay. Here's what the square root function looks like. 0, 0. All right. Because the square root of 0 is 0. Square root of 1 is, okay, and the next square root is 4, right? The next perfect square is 4, so the square root of 4 is 2. Okay. So if we think about those numbers, and then what? Yeah, then it would be 9 and 3 and so on. Okay. All right. So the square root of x minus 3. Okay. This is going to be a horizontal shift because that minus 3 is under the radical. Okay. It's not outside of the radical, it's under the radical. So that's the other thing. You know, where before it said x squared plus or x squared minus. But if it said, so if the other one, if it would have said x minus 3 squared, that's horizontal shift because the movement, the number 3 there is under the square root also. inside of that. Okay. So this means I'm going to move it 3 units to the right. Okay, 3 units to the right. So instead of being at 0, 0, I'm going to be at 3, 0. Okay, now think about that. If I put 3 in here for x, what's 3 minus 3? 0. Okay. If I put negative 3 in there for x, I get negative 6, and you can't do the square root of negative 6. So you've got to think about that. Right? So then what happened? Go over 1, up 1, go over 4, up 2, and draw my graph. So we have those same patterns that we can use to draw the graphs in. So when you're thinking about whether it's going left or right, if you're having a hard time with left or right, put both numbers in there, both possibilities in there, and see which one makes it true. Okay. So for instance, for h of x here equals square root of x plus 2. Right? If I put 2 in there, I'm going to get 4. Okay? Right? But if I put negative 2 in there, I'm going to get 0, which is what I'm looking for. Okay? So this is going to be a horizontal shift 2 units to the left. So my new starting point is at negative 2. Go up 1 and over 1. Put my point. Up. Go over 4. Up 2. And so on. And there's my graph. Okay, and this parent function is the square root. Quadratic, yep. All right, so there's horizontal shifts and vertical shifts, something you've done a lot of. Okay, reflections. All right, reflections. Once again, if it's affecting the whole function, okay, which is what the first one does, because it says negative f of x, that means we're making everything that's in that function the opposite, right? Because it changes it. So this is a vertical reflection. That means all the y values are going to change signs. The bottom one here, f of negative x, okay, that's a horizontal reflection because all of the x values then are going to become the opposites. So if it's outside the function, it affects the whole thing, or it affects the y values. If it's inside, it affects the x values. All right. Number 3, graph g of x equals negative x squared. Okay? So this means all my y values then, because it's in front of the whole x squared is being affected, that means it's a vertical reflection, so it's going to be over the x-axis. So then all these y values I have on here are now going to become negative. So I still have 0, 0, negative 1, negative 1, positive 1, negative 1, negative 2, negative 4, and positive 2, negative 4. And draw my graph. All right. Okay. Now, when we have, so this one it says the negative x, that whole thing squared. So think about it though. If you square a negative, what do you get? Positive. Correct? Okay. So what's going to happen here is that this is actually just the parent function itself. So if I was to reflect it horizontally, this means horizontal reflection. So what that actually says is that this point that's here is actually now this point over here. Okay? And the point that was here at negative 1, 1 is now at positive 1, 1. Okay? So that horizontal reflection, and let's see if I can actually get it to do it. I don't know if I can or not. So it actually looks like this then. If I redraw this, let's see how good my smartboard skills are. Okay, so this is what it's actually going to do, and it's going to flip it. All right, you see that? All right, it's a horizontal reflection, so it's going to flip it left and right. Okay, I'm just a little bit off, so if I moved it over here, then you can see it better. All right, so horizontal is going to, oh, get out of the way. Put it here. Okay, hard to tell where it's at, but so horizontally, it's going to flip it, and so you're going to get the exact same value here then. Okay, so here is the stretches and compressions part. Oh, yes. Okay. All right. Stretches and compressions. We're going to put it all together, and you'll have a pretty good idea when we're done. Right. Vertical stretches and compressions. Right. If it's vertical, if C is greater than 1, okay, that means it's going to be a stretch. We're going to stretch it out by that factor. The thing is notice where the C is here for a vertical stretch. It's out in front of the function. That means I'm going to take the whole thing and multiply it by that number. If it's greater than 1, then it's a stretch. If it's between 0 and 1, if C is between 0 and 1, then it is vertical compression. It's going to squeeze it together. Horizontal stretches and compressions. Notice where the C is at here. Okay, inside the parentheses, f of C times x. That means it's horizontally. But also notice that as I put this little point here, notice the fact that it's the reciprocal. So if it says f of 3x, that actually refers to a compression horizontally by 1/3. Okay, it's a reciprocal. What's the reciprocal of 3? 1/3. And if it said that it's by a factor of 1/5, then actually that's a stretch, okay, of 5. So if C is greater than 1, in these cases, it's actually a compression, because remember, horizontal things work the opposite as vertical. Okay? So where if I'm vertical transformations, if I say plus K, it goes up. But if I say plus H for horizontal, it goes left. Right? They're the opposite things. Right? Same thing with stretches and compressions. Right? For a vertical stretch, the number is greater than 1. But for a horizontal compression, it's greater than 1. So they're reversing. And the thing is, though, is that if you really think about it, vertical stretches are basically the same as a horizontal compression. Because as I stretch something out vertically, what's happening to the x values then? Okay, they're getting closer together. Okay. All right, so let's look at the vertical first. We'll put all this stuff together for you. All right, so it says graph 2 times the absolute value of x. So let's look at the absolute value of x first of all then. So let's see if it'll cooperate with me this morning. So y equals absolute value of x. Let's see if it likes me. Oh, how good is that? Oh, nope, it put 1s. Doggone it. All right, undo that. I don't think it'll do it. Okay. I'll get it to do it, though. maybe it won't do it for me. Doggone, I thought it would. All right, anyway. Absolute value of x looks like this. Over 1 up 1, over 2 up 2, over 3 up 3, both directions. Okay, there's the absolute value of x. So if I say 2 times the absolute value of x, since it's out in front of the absolute value sign, that means I'm taking all of the y values and I'm going to double them. So this y value here that says at 1, 1 is now going to be at 1, 2. At 2, 2 is going to be at 2, 4. Okay? I'm taking my y values and doubling them. 3, 3 would be at 3, 6. All right, and the same with the negatives.
So where's the base at? Were you saying at 0 still?
The origin, yep. All right, so there's the graph of y equals, or g of x equals 2 times the absolute value of x. All right, letter B. Here, once again, I'm going to draw the, and here's the parent function. I know the parent function in this case is absolute value of x. Okay? So when I ask for the parent function, that's absolute value. So h of x, it says 1/2. So that means I'm going to take all my y values and I'm going to compress them by 1/2. So instead of at negative 1, 1 is going to be at negative 1, 1/2. 1, 1 is going to be at 1 1/2. And usually what I'll do is in this case, I'll take the nice y values and use those instead of instead of using fractions, I'd rather work with whole numbers, right? Okay. So 2 would be 1, 4 would be 2, 6 would be 3. Okay. Those numbers are a whole lot easier to work with. It's because I'm putting them right on my cross pieces. You can do that. I'm just not a big fan of that. I mean, sometimes you don't have a choice. Okay? All right. So, really, okay, when you look at all of these, you've got the vertical shifts, they're pretty easy. Okay? Add some number, subtract some number, you move it up or down. Horizontal shifts are really pretty easy. Okay? You have to think of the opposite, move it left and right. Reflections, not too bad. Okay? Vertical stretches and compressions, those make sense to us. Okay? The one that's the hardest part is the horizontal stretches and compressions. Now, notice where the numbers are at. Once again, we have a situation, we have a radical, and the number is under the radical. That means it's something that's happening horizontally. Okay? And when we talk about horizontal stretches and compressions, it's always going to be the reciprocal then. Okay? So for the first one, it says graph g of x equals the cube root of 1/3 x. Well, I've put the parent function on here. The parent function is cube root. Because it's a radical and there's a cube, there's a 3 there. Okay? So it's cube root. And so here's what the graph of that looks like. Actually, that's only part of the graph of cube root, right? Because if we looked at it from the original, then we should have, it should continue on this way. Okay. All right, now, so this says cube root of 1/3 x. When it's horizontal, It's the opposite. Okay? So instead of me compressing this like it would be if it was vertical, I'm actually going to stretch it out so that I stretch it out 3 times as far. Okay? What's the reciprocal of 1/3? 3. So that means all my x values are going to become 3 times as big. So the 0, 0, is that going to change? What's 3 times 0? All right, so I'm thinking about x values here. Okay? I have the point 1, 1 on my graph. Okay? So the x value here is 1, and 3 times 1 is, so I'm going to go over to 3, and then I'm going to have that value. Okay? So the one that the one that was here at 1, 1 is now over here at 3, 1. Okay, I've stretched it out 3 times. Okay, my next cube is 8, right? Cube root of 8 is 2. And so if I wanted the next point where 2 would be at, where would it be at for the y value of 2 then if the x value is 8? No, it wouldn't. What's 3 times 8? 24. So my y value that would be at 2 would actually be way over here somewhere at an x value of 24. Okay. So the thing is it's stretched out 3 times as far, and so the same thing happens down here then for the other side of it. Okay, I have the point -1, -1, so it would be at 3, -3, -1. So it'll be down here. Okay. Right. So this graph is going to look like this. Is it going to grow as fast vertically? Okay, no, it's not. So think about it for a second. This is a horizontal stretch is equivalent to a vertical compression. I mean, they're not exactly the same, okay, but it has the same effect. Okay, so keep that in mind. All right. H of x, cube root of 3x. Okay, what's the reciprocal of 3? 1/3. So then this graph over here is going to be compressed by 1/3. So that means that the point here where it was at 1, 1 is going to be at 1/3 1. The point where x equals 3, that's actually going to be at 1. Where x equals 6, that would be at 2. Where x is 6 divided by 3 is 2. We are compressing it horizontally by 1/3. So I'm taking all of my x values and I'm multiplying them by 1/3 or dividing by 3. So the point that was here, okay, at the point 6 and just below the 2, right, would now be at 2 and just below the 2. Because the x value, I'm using 1/3 of the x values. Okay. 9, it was just above the line, so at 3, it would be just above the line. And that same thing applies horizontally, or for the negative sides. Okay. So this graph's going to look like this then. Oops. So notice, that graph is compressed horizontally, but what's happening vertically? It's stretching because it's growing faster. Okay. All right. So that leads us to, all right, so let's talk about all these things for a second. Okay, and this is the main page that we're going to use. Okay. And this is in the order that they're actually calculated too. Because notice I use 4 letters. What 4 letters did I use? A, B, C, and D, okay? And guess what? A, B, C, and D have a specific order for a specific purpose, okay? Notice where A, B, C, and D are, okay? Inside the parentheses here, horizontally, I have A and B, because things happen horizontally first before they happen vertically. So the actual order that a combination is going to happen is going to be A first, then B, then C, and then D. Okay? So when they ask you to write down the order of transformations, they're always going to happen in that order. Okay? Horizontal stretch or compression, horizontal shift. Vertical stretch or compression, vertical shift. Okay? So here I've written it down so you have a good idea. All right? A. And whenever we're dealing with combination transformations, or okay, a combination of them, we always want it to be in this form. Okay? We always want to be A times the quantity X minus B, and we'll talk about that more. Okay? A, horizontal stretch or compression. If it's between 0 and 1, it's a stretch. If it's greater than 1, it's a compression. We're using the reciprocal. B is a horizontal shift or translation. If B is greater than 0, it moves to the right because it'll say X minus B. And if B is less than 0, that means it'll say B plus, or X plus B. So X minus 4, the value of B is 4. X plus 4, the value of B is negative 4. All right? C, vertical stretch or compression. If C is greater than 1, it's a stretch. If it's between 0 and 1, it's a compression. D is a vertical shift or translation. If D is positive, it goes up. D is negative, it goes down. And then we have reflections. And this vertical reflection is talking about C. Okay, so if C is negative, all right, it's a reflection over the x-axis. If A is negative, it's a reflection over the y-axis, horizontal. We're at 33 minutes, Gibby. Yeah, and I'm probably going to throw it away because it's, I'm in the shade, or the shadows. Mr. Coffee in the shadows. Okay. There you go. Okay. So it's also here, right? But I like that there. So, okay. So number 6 is what we call a combination transformation. So first of all, here's the very first question then. What's the parent function? Okay, because we have this 2 here, all right? The parent function here is a quadratic. So what we're doing is we're taking this graph, taking this graph right here and transforming it. Okay, taking x squared and transforming it. Now, in doing that, all right, the first thing we have to do is we have to write this in this form. Okay, that's the first thing. Because if you don't put it in that form, then you can't see all the transformations that are actually happening. Because what we need to do is we want to tell what's happening in the process. So anytime there's a coefficient of x, you have to factor out that coefficient. Okay? It's not going to go outside the parentheses, but I have to factor it. So the first thing I've got to do here is I have to take out that 3. And if I take out that 3, what's left in the inside parentheses? What? X minus 4. 3 times x is 3x. 3 times negative 4 is negative 12. Okay. That's the first thing I have to do because this tells me my vertex is at 4, 2. And that's important because that tells me where I'm going to start graphing. Okay? So this is, let's talk about everything that's happening here. This means, this 4 means it's a horizontal shift by 4, vertical shift by 2, right? We've taken it from the origin at 0, 0, moved it over 4 and up 2 to start with. All right, so let's start with that. All right, so there's where my vertex is, at 4, 2. Now, what does the 3 tell us is going to happen? Is that a horizontal? Is that 3 horizontally or vertically? In other words, is it A or C? Okay, it's A because it's inside the square. Okay, so that's A. So that means then it's going to be a horizontal compression by 1/3. Okay, it's a horizontal compression by 1/3. Okay, and then what does this negative out front tell me? Okay, it's going to be a vertical reflection. So this graph is going to be squeezed together, all right, by 1/3 horizontally, and it's also going to be reflected. Okay, all right. It's a lot in one thing, Caleb. All right. He might give him inspiration, though. You could always use all the help we can get. All right. So, all right. The big thing is how do you graph this then? Okay. With your calculator, that would be great. Okay. I don't have a calculator up here that's working right now, so I can't use a calculator. So I've got to be able to do it otherwise. All right. So we need to think. Okay. Normally, if I had a table here, all right, as I go 1, 1, we're talking about here's x, and this would be x squared, right? Normally, what happens? Okay, if I go over 2, it goes 4. Go over 3, it changes by 9, 4, 16, and so on, right? Okay. The difference is now that instead of it going over 1, it's going to go over 1/3 because I'm compressing it by 1/3. So this would be a movement of 1/3. This is a movement of 2/3. This is a movement of 1. Okay, so that means I'm going to go where normally it would go over 3 and down 9. Now it's going to go over 1 and go down 9. Okay. So my numbers then are going to be, which I'm going to have to change my window here a second. Don't do that. So I'm going to go over 1 and down 9. So over 1 and down to -7, and both sides of that point. And down 9 units. Well, what did we say? We said it's compressed by 1/3. So in other words, it should only go over 1/3 to go down 1, only go over 2/3 to go down 4, go over 3/3 or 1 to go down 9. Okay, and that's not down to 9, it's down 9 units, Caleb. Okay, how many of you that somewhat makes sense? Okay, all right. So the thing is that you just have to think about, because this is a horizontal change by 1/3, that this number here then becomes 1/3 instead of 1. 2/3, 3/3, 4/3, okay, and so on. All right, so I'm going to go over left and right that far and go up or down that far to get that graph. I don't remember if I had that one. Okay. So the last thing you see is me reaching across my hand in front of the